It's a Euler style definition. Tamping it a bit. We'll have to cut that out.
Okay, got a full one today, and the thing I want to really do is go over the entire structure of this connection between two-state quantum mechanics and two coupled oscillators. The basic idea of the mathematics is there are Euler angles that determine the orientation of the sphere, but that is equivalent to determining a particular location of a spin vector. Imagine a vector inside the sphere here that can be spin up or spin down or spin anywhere. That is the idea of the Eulers. Now we're getting ahead. The Euler angles are described in Unit 6, and since we don't have more than 14 weeks, we are getting stuff ahead of time. As this isn't the first time that's happened, but most of the stuff that you see, the photographs and things, are in that, and I'll be handing that out. Or you can pick it up on last year's website. So what I would like to do today very quickly is just do a good deal of demonstrations of what this amounts to, how it works, what's behind it. And the first thing that might be a little bit of a mystery to you is why we would treat Euler angles this way. That is, we would first do a Z rotation, followed by a Y rotation, and then another Z rotation. So the crank that would set this ball here first does a setting by putting the this suction cup and crank down on the ball, which is located with all of these dials set equal to 0. So alpha is 0, that's the base azimuth dial. The beta dial, the thing that rhymes with theta, and that's the polar angle theta, really, for the spin vector. It's at 0 at this moment. But this is the last time I get to set the alpha. So assuming those guys don't move, here's my chance to set the gamma, the thing that is going to be the quantum phase or the overall phase of our oscillator. Okay, so I set that to some value, and then the next step is to raise the crank, and I'm still lined up, I'm approximately lined up with the y-axis. So this is the last time I get to, and this is the second rotation around y, actual y written on the base there, if you can see it. And at this point I set whatever beta I want without changing either the alpha or the gamma. The gamma is the one that's going to be associated with the phase. And then the very last rotation, and this is always available to this crank, is another Z rotation of the whole thing, azimuth. Okay, so that's the logic, mechanical logic between having this ordering here. And now we're going to do it with the actual operators that we worked out here, the sine, cosine, matrix operators to make first. This is the thing that's on the other screen, so I'll just briefly mention Z rotation, Y rotation by theta or beta, we always call it beta. And finally the azimuth, alpha for azimuth, A, Greek A, is the last thing you do. That's what sets that dial right there.
Excuse me, isn't alpha just 90 minus beta?
It could be, but it will be independent variable. It can be anything, those
How
two.
it could be in 3D?
We've set the beta to anything you want, and then we set alpha to anything that you would want.
So what is the reference axis for alpha?
The reference axis that it loves is the laboratory, that is the base. This right here has that dial embedded, that dial alpha, and you can see it in this picture probably a little better. That's the alpha dial right down there, which carries the whole apparatus. So that's our laboratory azimuth for this vector. This vector here will swing around as I change alpha and leave all of the others the same.
So,
This is the azimuth for the molecule, or whatever it is that lives in this frame that we're putting in different orientations. Does that make sense?
right.
And then the beta is the connector, you see, between the laboratory and the laboratory. I should put my hand down here, and the molecule, or whatever it is we're rotating.
Because over there, I thought on your left, it is just like a polar. Alpha looks like
Yes.
a polar.
Yeah, alpha, as I say, Greek letter A, first letter azimuth, right? That's what the phi is called when you do polar coordinates, okay? And then the polar angle, the theta, right? This guy rhymes with beta, but I've got to use different Greek letters to describe the state of this thing because I need the Greek letters to describe the operator. It also has a polar coordinate system with 3 angles. And that's what's coming next, but let's get the state down first. Okay, now, what happens with this rotation business is I want to do this to a quantum state. That's if we're going to do quantum mechanics, but I also want to do it for a two-dimensional oscillator. So I want to start, once again, with something that's lined up with 0 for everything, and apply the rotation that will change gamma. That's the Greek letter for gauge. Okay, if you want to know what gauge is, there it is. That is the gauge, although it's not strictly speaking the gauge, it has the dynamic phase mixer. We'll get into all that later on. But in any case, the first thing you do is set the gauge, just like the first thing you did over there was to set the dial gamma. And then the next step is this one right here. That's our rotation about y. And the representations of this for all of the angular momenta is always a real matrix, so that's nice. And then these guys, both the z rotation is complex, but it's diagonal. So there's a algebraic convenience that's had with this, as well as just making this machine here do something sensible. So the next step is to rotate the y, set the beta, and the last thing is to set the azimuth parameter alpha. So as we multiply these two together, we make a generalized rotation matrix for spin up with whatever amplitude that wave has. We could just put 1 there and be good for most of quantum mechanics, but we've got mechanical, classical physics that we're doing here too, so this is just an amplitude of a first component wave. So, what's going to happen here, you see, is that I've set this thing up right on the spin up coordinate. There's the arrow to indicate it, like we talked about last time. And this has got 0 right here, so I could just erase these numbers. I'm only interested in those two numbers right there. And that is the way we will characterize our phasor x1 plus p1, the first phasor, which has a real and imaginary part. And we're talking about position and momentum when we get right down to this, as I've explained already. And then the second component, same thing. That's this thing right here. So there's an angle here, beta, And if you're talking about a laser getting pumped up from spin down to spin up, that's called population inversion. So this beta here serves as a population inversion angle. And then this is a relative phase. This is the phase that's seen, if you were to think of this as a something of this alpha here to have a shadow on the plane here, that would be what people that were living in the laboratory would be happy to call the phase. That is the relative phase. But the gamma, this is the one that if you imagine somebody living in this ball here, in this electron or whatever, it's something in there that could see the outside world whirling around, this would be their azimuth. We don't respect it. We're laboratory people, so we just leave it as this mysterious outer phase. And phase is very mysterious, as I'm going to show you later on. Anyway, that takes care of coordinating the location and the state of this system. Now, literally the quantum state of a two-level system, but for us it's orientation of the spin vector, an arrow inside this little sphere here. Eventually we're going to make it transparent. Now this is stuff that we didn't get to in the last lecture. This is where I take this generalized, call it SU2 because that's what it is. It's actually unitary 2 without the S, if we've got this hanging on there. And that I want to make a quadratic form using this generalized amplitude, A for amplitude now, 1 and 2 of the two-state quantum system, or our oscillator. These are complex phasors associated with two masses that are coupled to each other. And the idea here is I would like to see a quadratic form for the sigma A, that's this matrix, the sigma B, that's this one, and then the sigma C, that's the weird one that makes things go. It's colored green. This right here is the reddest of them. That's the one that makes a standing wave that never goes anywhere except this over to here. This is the one that's balanced. This is the what we're making here are names for expectation values, if this is quantum mechanics, of these three operators with respect to this would be psi1 and psi2 if it was a two-state system. So both of these are complex amplitudes, as you're indicating right there. So we go ahead and work out what happens here, and I get a number of different results. The first one is I get this A1 star A1, A2 star A2 times a half. That's the other thing I'm doing. I'm just working with the idea of these as spin vectors, and so spin angular momentum, so that the half is the half quanta that comes with a two-state system, like an electron spin. And then if I go ahead and flesh this out, put in the x's and p's, what I get here is the difference between a harmonic oscillator energy x squared plus p squared for the first oscillator, or the first quantum state, and then I've got an x squared plus p squared, but it's being subtracted. There's a difference between these two. So this is kind of why this particular operator is measuring the difference between the energy of the two oscillators. And then if I go ahead and I put in the polar angles, the Euler angles, alpha, beta, and gamma, gamma is going to disappear from this because of either the plus I gamma cancels either minus I gamma and just give 1. So we won't see any gammas when we get all done here. The things will disappear. This is what you get in the final result here. You get a cosine of beta here, you get a cosine alpha sine beta here, and you get a sine alpha sine beta here. So you just get polar coordinates based on alpha and beta. The gamma goes away, cancels out. So that's basically all I need to say, I think, about this. funny names. Chirality, because this is the one that the C-type operator is the one that's going to make things go around. Current, cyclotron, Coriolis. We'll see all of that when we start working these things. And then this one is we'll spend some time on that one again too, although you've seen it already. Now let me just stop for a minute and say there are really three main ways that are used in the literature to picture U2 things. And I'm thinking of quantum computers that have qubits. So we're doing the mechanics of qubits here and looking at them a number of different ways. The crudest way is just what you would do if you were talking about two coordinates of an oscillator. You just make a trajectory in there. It might be a Lissajous pattern or it might just be an ellipse, but whatever. That's really simple. You just write the real parts of these two component waves. Okay, that's fair enough. But boy, that sure covers up a lot of things that are happening here. This is the opposite extreme. This has all the information that that particular qubit can give you. It has the real and imaginary part of the first state and has the real and imaginary part. So all four dimensions, those are real numbers now, are present and accounted for. Okay, so that's an important picture. Now, it's still hard to visualize. We don't have brains that think in four dimensions, at least not yet. Maybe we'll grow them as time grows. But right now, this is a three-dimensional room, mostly three-dimensional students, and very definitely three-dimensional professor. But at this point, if I can go and just see where this spin vector is, and then read off the gamma as the last step, I've got a really good visualization tool, and that's why the quasi-spin of a qubit is important. And it has polar coordinates, which are given by that. So that's all there is to the notations that goes with keeping track of the spin vector, the state of the qubit, if you will. And it involves four numbers in all. It's a four-dimensional thing. And in fact, this stuff is going to work for relativity. That does Lorentz transformations too. That fourth dimension is kind of been lopped off here. So here's the idea. General spin state is a rotation operator of spin up, and that makes all of it. All of the possible states that you can have are accessible with all three numbers working. So that's an important thing. I say notice phase or gauge angle is killed when you go down to the subgroup R3, the rotation group, and you don't see it in this picture right there. So one of the things I want to show today, and it's a little bit hard to see it on this one, but I want to show that the polar coordinates for the spin vector, which is going to be flopping around in there, and right now it's just kind of pointing at you out of the screen there. It has an azimuthal angle, 2 phi, that is exactly twice what we're going to be calling the Faraday angle when we look into the x1, x2 plot of the four dimensions, x1, p1, x2, p2. So we will be making an ellipse in that has it tipped an angle that's circular dichroism is what they give the name to when the polarization starts to rotate for some molecular solution or whatever. Chemists use this a lot. But physicists are a little late coming to the game there. And then the aspect angle of the actual ellipse, that's the psi here, that is the, twice that is the polar elevation, the polar angle, if we were using the C as a z-axis, would be right here. This is a complement of that. 2 psi is a polar elevation, and half of that, remember, this is the three-dimensional world, this is a two-dimensional world, this is going half as fast, so all of the angles here are half the size of their corresponding polar coordinate. And then the third angle, the actual phase on the ellipse is just encoded in that dial gamma that goes with the S vector and the sphere. So this is something we're going to start to get used to today. In any case, this isn't something that is just brand new. This is really old, although it was never done quite as completely as this. John Stokes has his name on the Stokes sphere, and I believe that the vector S comes from John Stokes. This is 1865. It's about the time the Civil War of this country ended. And he came up with basically the arithmetic that I'm talking about here. He's using Hamilton's quaternions, so it's kind of a mess. And if you go back and read the papers, they're really kind of hard to read. But we're trying to make that so they're easy. So this is easy. Anyway, this is a summary of what we've got right now.
Sorry.
Yeah.
Is that not also referred to as a block sphere in some of the literature or computer classical?
Felix Bloch had very little to do with polarization.
Could have swore I'd seen
Felix
it.
Bloch is fairly recent. I don't know.
This predates it, so
I mean,
I'm not trying to argue away. I'm just saying if you're reading up on the QC
I mean, call it a
side.
Feynman sphere. It could be called a Feynman sphere, right? I mean, there's a heck of a lot of people that worked on this thing since 1865. You see, but John Stokes the first one. Very very sure of that. Okay. Then there's Euler and a bunch of others that got involved too. So anyway, whatever the name is, give it your own name. You're gonna maybe do some work on it, so you use your name on it too. Anyway, the idea is that there's the U2 world, and that world is probably best described by oscillating orbits in a two-dimensional space. If we're thinking classical mechanics, a polarization ellipse, if we're thinking of photon mechanics, something else that corresponds to whatever an electron's spin is doing, and its phase. So basically what happens here is every possible elliptical state, and that's the idea, is every point on the sphere that this spin vector points at corresponds to an entire ellipse. And if you want to put the gauge on it, it'll tell you where on the ellipse you are. That's the overall phase at work there that you have to know. And that takes care of the states of this thing. In the R3 world, it has a sphere and this machine here. This, of course, is where all the information really is, x plus I P1 and x2 plus I2. Remember, again, this is a four-dimensional object. This is a three-dimensional object, but if you can have a gamma dial, you've got knowledge of what's going on in there. So anyway, that I want to make clear of the ways to represent this very important qubit. The U2 group theory is behind it. And there's another way to look at it. This is where the angles are now shown rather clearly. The azimuthal angle of that that we have down here characterized, that is equal to 2 times phi, whatever phi you want to characterize by using ordinary polar coordinates. Now we don't use theta, we use the complement of that, and it's 2 times that. It's 2 times this angle right there. That's the aspect ratio, and then this is just a rotation, a slant, this tipping angle, alpha. And this over 2 is what would be the phi for this ellipse. And then the ellipse's shape is determined by that one, and that's the polar angle. And as you get closer and closer to the C, you get closer and closer to having circular polarization. If you stay in the horizon, the ellipses are all flat. They're just planes, oscillating lines. We'll see all that coming up. So what I want to do today is play with first an A Hamiltonian, pretty dull thing. It's diagonal but off balance. There's an A and a D on the diagonal. A stands for asymmetric diagonal type of like, or whatever qubit you're going to be playing with. And then as you come down to the plane, you'll be seeing, as I say, plane polarization all around the equator. All the rest of the sphere, except for this point and that point, is devoted to ellipses. Well, there's an ellipse. It's very perfect. It's a circle, either right-handed or its opposite is on the other side, is left-handed. And this guy right here is 45 degrees oscillation, and it's orthogonal to 45 negative 45 degrees oscillation. And the same thing goes for things that are somewhere between 45 degrees that are on the equator. So the sphere's got a lot of stuff on it, and it's making it easier to visualize the dynamics of going from one state to another and how you get there. And that's basically what the homework is that I've given you. The most fun part of it is to do that. And then here's another symmetry that an operator can have, where you have a matrix that's diagonal but equal to, I'm sorry, not diagonal, but anti-diagonal, and this balanced. That is, you have the same in the upper right hand and the lower left hand. One number, B, that determines how fast that crank goes. And that's the one that we're going to spend more time on, because that's actual coupling between things. The A, coupling's gone. B, that's the most complete coupling that you can have that's real. And then there's this guy, the make thing curl crank, the C-type thing. Literally is going to be rotating everything. Ellipses or lines, whatever, they're going to get rotated by that one. So these are all links that work. I'm going to come back to them after we do some more secretarial work that's necessary to make this stuff useful. That is, how do you handle the Euler angles, but also, and this is the thing that's really screwy, is that crank has polar angles too, plus it has an angle that it turns with. So we've got 4 degrees of freedom to play with in the operator space. We've got 4 degrees alpha, beta, gamma, and an amplitude in the Euler description. So we've got some stuff to do here before we get going. In any case, that's what I want to do first, is I want to make a connection between the spin vector has these 3 components. If it's a unit spin vector, I don't put anything else on this. I just have alpha and beta. I forget about gamma for a while. But really, you're going to have to deal with the whole thing if you want to. All 3 Euler angles are important. And then the operator that's going to move the states around is this machine right here, this thing right here. That's going to be at a certain azimuth, okay? There's the azimuth, is a script phi, okay? I'm being as careful as I can with the Greek letters here. Remember, the spin's already taken care of by 3 angles. The azimuth alpha, the beta dial for the y rotation, and then the internal and total phase angle, the gauge, is what's being carried here. But what's going to work on it, and we'll have little suction cups, as you see, to put down on this thing and turn it, and then maybe put it and turn it. All of the operations that you're going to do to qubit is going to be described by these 3 angles. Phi, axis angle scale, and there is a scale right there that has that well marked off. A theta angle scale is this guy right here. And then finally, how much do you turn, okay? The uppercase theta, which is going to be the uppercase omega, that's an angular velocity times time. And that's the thing the Hamiltonian provides. So this is describing the Hamiltonian that's going to work on this state. So it's these kind of angles versus these kind of angles, we've got to relate them, or we have a disaster here. All right, so let's get started with that. And I'm going to go ahead and put this guy up here just to have a reference. And then on the far screen, I'm going to put the alpha, beta, gamma stuff. And on the other screen over there, I want to get started on putting some of the theta stuff as well. So this is just to show you what we're dealing with. I think I'll stop actually right here with this one. So this is where we're going to do the work on putting these guys together, and then that's what's involved in putting them together. So here's the deal. Now this is something we were going to cover in the last lecture. We didn't get to it. Now we can't put it off any longer. So here are the 2x2 matrices, the spinor rotation operators around z, y, and then z again. We don't show x here. X is a weird thing that's both not diagonal and not real. So we don't work with it much, particularly, well, we've got enough work to do. We've got to keep things as simple as possible. So anyway, here's the rotation operator, the whole thing that would work on any spin state, fore and aft. And this right here, what I've done here, is something that's really important, and that is to expand this matrix in terms of the things that we're working with here. Well, the unit, and then the anti-unit, that is the A-type matrix. This is the, I just call this the zero unit matrix, or origin, if you will. And then there's this guy right here, and then there's good old balanced guy there, sigma B, that's sigma X in Pauli's language. This is sigma Z in Pauli's language, this is sigma A in our language. And finally, the craziest of them all, the curly one, the one that Pauli would call Y. This is the only one that is got imaginary numbers in it. The other two are real. Stay on the horizon, you don't have to worry about the funny things that have to do with rotation. In any case, rewriting this entire matrix in alpha, betas, and gammas is a good description of a state, and that's the point I want to really make here, is that the alpha, beta, gamma make better coordinates of the state. These things are terrible coordinates, and you'll sort of see why in a minute, but they're really great coordinates for operators. Okay, so here's the stuff that goes with looking at the state of the thing, and let's remember physically what we are. Phase coherence angle, that's the name that's actually given in most literature. Population inversion angle, it's pretty common. Overall phase angle, okay, the gauge, if you will, are all tied up in describing the state, where the state is, the coordination of the state. Okay, but where's the operator? That's what those angles take care of. They have to be connected, you see. They have a combination here. When I take the rotation matrix that goes with this thing, and I use brackets to describe the three angles, even though we won't mix alpha, beta, gamma with italic phi, italic theta, and then uppercase theta. Uppercase theta being that guy right there, which is connected to omega times t, omega being angular velocity around the crank. So this matrix right here has doing the same thing. It's doing a rotation that this one is doing. But how do you relate the alpha, beta, gamma to these three guys here? How do you do that? That's the thing. In other words, this matrix right here is equal to this one if we're talking about a particular state this thing represents. Now, we'll do that in a little while. I don't want to say any more. It's a little confusing. Anyway, just as this one has collections of sines and cosines with half angles, this thing's got full angles. It's living out there in ordinary space, so to speak, three-dimensional space. Okay, so that's what we have to do. We have to go ahead and look at this thing, and I'm going to write down each one of the 4 dimensions in the phase space, x1 and then p1 and then x2 and then p2, right here, and that's what we will use to put these together. Because I can pull those things off from this expansion and just set them equal to the corresponding ones on the other side. So this is a really complicated conversion from basically Cartesian coordinates to polar coordinates, if you want to call it that, but then some people would say those are more like polar coordinates. These are weird. Okay? In any case, that's what we got to solve right there. And that's a job. And we're going to rush through it because we don't have all day. It takes about all day to sort this out, to give me a formula that relates those angles. Here, alpha, beta, gamma, and here these phi, little theta and big theta. Okay? Well, it doesn't take much. I put little guidelines in here. You should study this on your own, and when you get done, you have some formulas. First of all, give you alpha and gamma. They're not so difficult, but we still have to do a little bit of thinking to get beta. And these arc sines and arc tangents, if you're going to put it on a computer, you'd better use arc tangent 2, because you need to know what quadrant you're in. You need to put in 2 variables to specify that. I'll say that again when it becomes important. Now, the inverse relations, I just take these things, and if I'm not too difficult, if I'm not too careless, I will come up with a relationship that gives me the Darboux angles in terms of the Eulers. This is the other way. This is alpha, beta, gamma in terms of the Darboux. Now, where does Darboux come from? Darboux is a geometer. If you've taken differential geometry, which I haven't, but I've read books on it, and Darboux is featured strongly in there. Darboux is the guy that realizes that if I take a sphere and rotate it arbitrarily, there's still a line of points in there that are exactly where they were before I started the rotation. Now I rotate it a little bit more, that line moves, but there's still got to be a line somewhere. That's kind of a head scratcher, right? Well, that's what it amounts to in the sense of using a crank to rotate. There you know very well that the crank arrow points at the lines that aren't, the dots that aren't moving. Well, they're twisting, but they're infinitely small, so we don't say they're moving. Okay? Now, this kind of thing is the way mathematicians like to think, and physicists don't often follow them. But for example, if I take a road map of Fayetteville and put it down here, there is a point on that map that's exactly where we are. Right? Okay? You got a microscope and say where you are. Okay, it's a little different from where I am, but you know, the 2 points are real close together, right? Then we slide that thing, right? There's still a point that is the same on the map as in the thing that the thing is mapping. This has a whole line of points that are doing that. This sphere does. Okay? Darboux's vector is basically the omega vector. When you talk about angular velocity, omega, that's Darboux's discovery. Long before it was really used in mechanics. It's different geometry. Okay, well, let me point out what goes on here. After you get done with this, you really ought to check it. Okay, so we're going to look at an example where I set the Euler angles for this gadget to 50, 60, and 70. Okay, so I'm going to set the dials 50, 60, 70. I'm going to do a picture of it. Maybe we can actually do it. And then I calculate using the Darboux conversion formula of this 50, 60, and 70, and I come up with 80 for the azimuth of the crank, theta of the crank, that's this angle right here. Azimuth is on this plate, crank is on the bar, okay? At some theta, okay, that comes out to be 33.7, and then 128.7 is what the crank I had to turn in order to get this to happen. So you should put that into the formula that goes the other way. Take all of these angles, these Darboux angles, and stuff them in the formula here and see what you get, okay? And you see what we get is 50.007. Well, that's just because my calculator didn't go and put three-figure precision in there. I got basically 2 or 3 figure precision. But anyway, I get 60, 70, and 50 where I should get for alpha, beta, and gamma. So you always want to check that something as complicated as this is giving you the right answer. And you also probably ought to realize that you should use A-tan too. Anyway, here's the idea. This is where I set this thing up, and I'm going to come around here and see if I can get it to work very quickly here. I'm going to have to come out there and see that I get 31.7. That's what I'm looking for on the preceding slide. Let me go back here to the thing. So I need to set this thing up with 33.7, and I can just barely see 34 on the arm here, but let me just go ahead and see if I've got that right. I've got 32, 34, 32, 3, that would be about right there, okay? And then I've got to set the azimuth of this thing. I can rotate this thing to exactly 80 degrees. That's the phi, okay? And I'm pretty close there. I set this up before class and it hasn't moved that much. So we're in pretty good shape. And then what else do I need? I need to set this thing to 0. Okay. So that what I'm going to do is I'm going to apply a rotation by 128.7 to this ball here. Now, when I set this thing up so that everything is 0, there's a 0 there now, and then I've got to get a 0 over there. That's on this side right here. I've got to get 0 on the alpha, okay, and 0 on the beta, and then I can arbitrarily set the 0 on my crank here, because I'm going to simply compress this guy here like that, tighten it, okay, and you see I've got what's called Gimbal Lock at this point. This is what killed a lot of pilots that were using in World War II, gyros to fly, around and try to stay alive. And you get a gimbal lock, the gimbals start turning and the gyro stops, and you're dead, because you absolutely need that gyro to find out where the hell you are, especially if it's cloudy. So that's what this is. I can move this thing right here. Alpha and gamma cancel each other. And this thing will not turn here, okay? I mean, it would make this thing go infinitely fast if it was absolutely perfectly conducting. But right now, I can break free. Now what I'm going to do is I'm going to turn this thing, and I set the dial here carefully to 0, and then I'm going to turn it 128 degrees, somewhere in that neighborhood, okay? And that means I bring the thing in here so it can rotate, so I can unlock the gimbal, okay? And then turn this thing to about 120 degrees or so, okay? And according to that, I should be getting close to having the Euler angles 50, 60, 70. Okay, 50 for the alpha, okay? And you can come up and check on this. It's not too bad. It's off about 5 degrees or so. And then the 60, I should be getting something close to that. I'm right on there. And then finally, the 70 should be showing up for the gauge. And not, let's see, not too bad. Should be looking in that thing. Anyway, the idea is that we have turned our this sphere to this arbitrary rotation, and let me move to go ahead and get this slide back again on this machine right here. Okay, I'm at this point right here with those coordinates. Okay, I've got let's see, theta 128.7, and that's giving me an alpha, beta, gamma of 50, 60, 70 right at the, you know, if everything was perfect. So the idea is that the line of points that crank is pointing at are in exactly the same place they were here, 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 and will continue, you see, to be in the same place in the sphere. That's your Darboux that's your Darboux axis. That's the crank axis. That's what crank is. Yeah, Jake.
On the previous slide, when you were setting up all your angles, you would set up,
Let me go back.
or the slide right before that, down at the bottom where you set theta equal to 33. Is there any particular reason why that's actually over on the, where you
I
actually
set
have
that
the,
right here.
but
yeah.
the blue letter that you have associated with it isn't
Theta.
actually the theta?
Yes.
You have the theta associated with the 128.
Yeah. It's
They're
pretty
both
close to
blue.
it on this picture here. It's actually photographed pretty close to that. It's right in this neighborhood. See that little digger there? That's what I set right there. See it?
Okay.
30, 32, 33, and a little more. We're not talking six-figure accuracy here, right?
Oh, so that's,
We're lucky to get two.
okay, I may have just been misreading it, so that's a lowercase kind of weird
Thetas.
script theta. Okay.
Yes.
Um,
Script.
Yeah. Just doesn't
Or
look like
italic.
the normal lowercase
Yeah.
theta that I see that actually kind of almost
We're
completes
running
that
out
circle.
of notation. I think we're going to start using Chinese pretty soon.
Yeah.
Okay? Does that answer what you're after?
Yeah.
Okay, so what happens here is this continues. Okay, I go past my 120 or whatever it was, and just keep going here, okay? Just keep going, right? And look at what I get. I have rotated that guy through an entire 2 pi. That ball has been rotated 2 pi. But we're not home. Remember, that's what spinners do, right? They're half as fast as the 3 by 3 world. So this thing goes down to the end here, 300, and then I get 360 right at this point here, okay? This thing is on the other side. The dial of the beta is hiding behind there right now. It comes out, it comes around, okay, and bingo, there it is hiding under the bar where I can continue. I can continue going now, and I will go ahead and do that, and then I'll try something. I'm going to go fast and see if I can keep this thing from falling apart. But here is the other complete rotation that is necessary to complete it for a spinner. Okay, so this mechanical device is really feeling the 4 pi world, the 2 pi world that we live in. See, if I go like this, I've gone 2 pi, and you know, I'm not a different professor, right? Well, I might be. I could be crazier on after this, so I better go back and straighten myself out again. But anyway, that's the whole idea, is that I need to go around twice in order to get home. And an electron definitely has to do that. And these oscillations that we're doing with the two pendulums is definitely doing that. So this is a very peculiar sort of thing. I'm just going to try it. It doesn't usually work, but usually you can make this thing go around and around. It used to be I could do this very easily. It's working very well today. But the carriage there is really important. And let me go ahead and show you some inventions that have come about because people realized this. This is in Scientific American, 1975. It was completely ignored. But it shows a way that in your laboratory you could set up something that put power in there without a commutator. That means you could put noise-free power into something on a machine there, as long as you had something like the carriage there to go around half as fast as the rotation, and that's what these gears are for here. So I run a wire up through there, and it can go around a million times, and this will never get tangled. It'll get stuck here and stuck there, and come back again, okay? And then here's where you do it with actual beam of light. So you can make a periscope where you look into a rotating frame as though you were there. Okay? Now you think, how many people here, just out of curiosity, have heard about this, the fact that this happens? It's, you know, we're supposed to be physics guys, and we should know the mathematics that's behind this, right? And very seldom we don't. Now, where else is this? Let's say I have a cup of acid and I don't want to spill it. Okay? So what I'm going to do is I'm going to rotate this thing, I hope, without dislocating either my elbow or my shoulder by 2 rotations. Okay? And you can tell by the handle where I'm at. All right? And I'm come around, and without spilling the acid, I'm going to come around again, and I'm back. But it took 4 pi to do it. Okay? Every high school majorette knows this. And that's what they do with their baton, to make it look like you're rotating. Okay? Aren't you ashamed of yourself? You don't know what a high school majorette knows, and you don't know mathematics? You got to catch up, right? Isn't that, I mean, that's a piece of mathematics and physics that we can't ignore anymore. All the qubits do this. Okay? Now, I'm going to rush through this particular thing. This is just some mathematical secretarial work. I've given you a problem to just explore this a little bit. But this is what I say is a quick way to find eigensolutions of this matrix. Okay? I go ahead and I look at the thing, I do the expansion that we talked about, angular velocity times angular momentum, angular velocity times angular momentum, 3 components of that, plus something that's really simple, a unit operator. We're not doing relativity here, so we don't have to do anything with that. It can just have its own value. But there are 4 parameters here, these 4 and then that, and those are all things that we can set on our machine, or we can set A, B, C, and D. There's 4 letters that are important here. So the sum of the squares, that's the actual angular velocity. This is represented by this Hamiltonian, and that's what it's going to do when it gets to be an exponential. It's going to derive it at that frequency and give you an angle going that way. And the eigenvalues, and this is what I want you to do in the problems I gave you today. Whenever you solve a 2-state system, I would like you to take the solution here, which you recognize is coming out of some kind of quadratic equation. We've gotten that automatically, but I want you to diagram a 2-state system by putting its 2 eigenvalues and the average of them, okay? And here's where the 1/2 comes in. Remember, omega over 2 is what the spinor does, okay? It does plus omega over 2 and it does minus omega over 2. Altogether, the splitting is the beat frequency that engineers use. But omega over 2 is what sits on the sum that gives you the highest eigenenergy, and here's the lowest eigenenergy. So this diagram, we're going to use that as we talk about both the classical and the quantum mechanics. It's frequency, and frequency is energy in quantum mechanics. We'll talk about that at the end of the course. But anyway, here are the polar coordinates that this has. And what do you do to find the eigenstate, the eigenvectors? And remember, I said more information in the eigenvectors often than the eigenvalues. So we've got to do this carefully. Right down to the phase, if you will. But usually that's kind of floating and free until we start doing quantum computing. Then it got very important. So this is just showing you what you do. Step 3 is to find eigenvectors. Replace the Euler angles, alpha, beta in particular, of the Euler state with the Darboux axis angles, phi and theta. And why would I do that? Well, the answer is that I would simply be, and I'm just going to screw this thing all up right now, if I was interested in finding out what's the eigenvector of this particular crank, well, it's right there. I'm just going to put the z-axis of the ball right there on top of the thing, okay? Screw it down, tighten it, okay? And then I can turn the crank as much as I want, and if I've done it right, the other angles won't change at all, right? All I'm doing is twisting the phase. So there's an eigenstate, and the rotation of the phase is the eigenvalue, basically. But that's not all. This thing doesn't do this very well, but I can also turn the thing completely over and put the suction cup there rather clumsily, and then I turn again, and that's the other eigenvalue. It's got and the other eigenvector, okay? So that's more Darboux stuff. If I can put the device here, I can put my spin vector pointing at the Darboux line, all it's going to do is twist, which means nothing. But there will be phase. The phase will be running. The gamma will be turning with this. Okay? So that's what's going on here is I make the omega line up with spin vector that I have. I replace that, and then I figure out what these angles are going to be. And you got to do it the other way in order to really finish this. Okay? Now, a lot of times in this calculation, I'm taking arc things. If you're programming this, definitely want to use A10 too and give it two numbers, not just one number that a ordinary arc tangent asks for. All right. Okay, we're almost to the point where we can play with this stuff. Here's an actual example. I'm asking you to do this by projectors just as an experiment to see how it compares with doing it with geometry of Darboux. Okay, here we go. Let's go down the line here, and we'll start here with the A-type motion, just to get familiar. What does it look like? We're going to go through A, we're going to do B, and we're going to C, and then we're going to do them together. And by that time, you'll be dizzy enough that you want to get the hell out of here. But basically, I'm going to draw this diagram of the frequency that is being played out here, and I'm going to go ahead and use the simulation that's available on, and this is not a terribly fast computer, but I don't need real speed for what we're going to do here. In fact, I'm going to want to slow this down. But this is basically what we're talking about here. We're talking about two oscillators that have nothing connecting them. That's the A type, right? It's completely diagonal. One of them has frequency A and the other one has frequency D. And that's all there is to it. That's A-type motion, okay? When you're on that axis, that's what you're getting. Now, let's go ahead and slow this down a little bit because there's still a lot of mathematics hiding in this thing. If you want to slow things down here quickly, do something with the exponent here. Reduce the exponent from -3 to -4. Okay? And while we're at it, let's just go ahead and erase the paths and maybe reset t equals 0. Okay? Now, let's just go ahead and do what we usually do and start our initial conditions right here. This is the first component of the A-type motion. Really exciting, isn't it? It just goes back and forth. This thing never knows that anything is going on down here, right? That's what you get when you have a Hamiltonian that has A and D on the diagonal and no coupling, right? And it works the other way too. If I want to go here and start this guy, now he's going to do stuff, and this guy doesn't give a darn. He not connected. No coupling. Right? That's what asymmetric diagonal means. A, D, and those parameters, A and D, that's the way to remember. what they are for our way of looking at things, okay? So there's a spin down the a-axis, there's a spin up the a-axis. Those two states are orthogonal over here. That's the three-dimensional space, remember. This is A, okay, axis, right here. Okay, he owns that whole line, plus and minus of the A, or Z. This is the Z poly spinner, right, the one that's diagonal. Okay, so, all right, but still it makes pretty patterns that are given by a continued fraction. We'll talk about that with respect to the B motion. But in any case, it's just the ratio of the frequency in this direction, up and down, and the frequency in the other. And so if I go here at about 45 degrees, it's going to curve. You can see that the potential that goes with this thing are quadratic forms. The ellipses are lined up with their eigenaxes as the x and y axes of the ellipse. So we get really beautiful curves out of this one. It's just that the envelope of the curves is not rotated. It's right there on the axis frame. Does that make sense? Okay, so this is a trivial case, you might say, of our possibilities for motion. Okay, well, let's not waste any more time on it. I will go ahead and pause this, get back to the lecture, and continue to the next stop here. Now, this is a picture of what we just had. There it is all lined up there. And I want to go to B motion now, okay? The balanced B-type motion. That means that we're going to be rotating now around the B axis instead of the A axis. And I've turned the A up. It is Z Pauli, so this Pauli would put the Z here probably in a diagram. So this is, you know, paying attention to that orientation. And here we have two orthogonal states. One is going to be a slow mode on the 45 degree and a fast mode on the negative 45. That's the way we set it up here, with a minus B. This is a negative B, so my crank is not here. In most situations, you have a negative number, and we'll maybe talk about why that is. But certainly it's true when you have a spring coupling. Okay, so we're going to have a slow motion here, relatively speaking, and a fast motion there, okay, when we get to do this. And so we've seen this already, but let's do it again. This is going to be a rotation that takes a spin vector, and we're going to start on the A-axis, which is as far away from the two eigenstates, orthogonal states for the B eigen solution, and we're going to crank around, and we're going to, this is the crank this way, right-hand rule, we're going to go this way. So very soon we're going to hit the C-axis, and we're going to see circular polarization. I'd like to show you that the particular simulation that I've got set up right now is going to look more like that. So let's just come back here and go ahead with putting this thing into that motion there. I will click on this and hope for that. Yes, there we go. Okay. So this is a type of motion, and let me just do it real quickly here, that has a slow sort of motion, slower. This is the beginner slope, but it isn't too different from the advanced slope. Okay, and I can just go ahead and erase all paths just to make that clear. There's that, and then compare that to this one, where they're opposite each other. Okay, that's clearly a little bit faster, right? Well, we've got a pretty small B coefficient here. We got 0.2 there. That makes it so that there isn't much difference. This thing is only a little bit oblong in this direction compared to this direction, where the lines are closer together. Okay, so all of the motions that you get with this thing, and all of the stuff that we talk about that comes on here, including the Lissajous patterns that are characterized by continued fraction calculation. Okay, and we have that nicely cataloged in just a minute here. But you see the beats. Okay, an engineer would say that's a whole beat from there to there. We say no, you got to go down and come back. That's the beat period that we see. It's half the frequency of what an engineer would say. We have to worry about phase. That's the whole name of the game in quantum computing, and will continue to be until either the industry collapses or we really get it to work. So there goes that, and I'm going to come out of this quickly here after I have paused it. Don't want to use up things. And I'll show you real quickly a couple of things that we just we'll show the canned versions of what you just saw. And there's the total beat frequency, and there's the half that goes with that frequency, and then there's a minus a half that goes with that. Half sum and half differences are very important in this business, especially with two states. But here, this particular simulation is the same as the one we just looked at, and what I want to point out is that when you do this simulation and you let the thing go all the way through 2 beats, 2 engineer beats, you get back home. But if you only go through 1 beat, you end up here, pi out of phase. So let's just see if we can reproduce that real quickly here. I will go ahead here and click on the actual simulation. And so there we go. And I'm going to wait till that Stokes vector comes to, and I'm going to stop right there. Ooh, I missed it. Let me go ahead and reset t equals 0. I'm going to do something else here because it really would help to see this in slow motion. Okay, so I'm going to slow-mo this by making it 10 to the minus 4. I'm going to reset, I'm going to erase the paths, reset, t equals 0. Okay, so here we go. I started with a Stokes vector on the thing, and I'm going around, okay, and I'm making a beat here. Started at 0 here. I've got a pretty good peak there. This one is just starting to 0 out, okay. Now, sooner or later we'll get back. I don't know why I don't have a line going from the A. I thought that's where I started. But let's see what happens here. So here's where I started, okay. And
You were in between A and C symmetry there, because it's
there we go. Yeah, that's the pi right there. That's where I would start. I should have started this thing. Let's see if I can do that again. Pause. I'm going to erase paths. Pause. Reset t equals 0. And I don't know why that spin vector didn't.
you're not on an eigenaxis there. You're
Yeah.
in between A and C symmetry for that initial state.
Yeah.
Started on a diagonal manually and watch.
Yeah, I'll that doesn't necessarily get what I want, but it doesn't show the spin. I will now try to. There we go. Okay. I'll go.
It was glitchy there.
Yeah, it's probably not. I'll go ahead and crank this up a little bit so it goes a little faster. So we're passing C now, and we're making circular a circle there, but we didn't get to finish it before we're off of it. And now we're doing up and down on this axis, not the axis we started on, the x-axis. And then we turn the corner down here. Now it's a left-handed circle right now. It is the perfect arc of a circle there, but then it gets screwed because the S is going so fast that now it's coming. And at this point,
It's virtually linear there, almost linear.
pause. I'm just a little pissed, but that's the pi I'm talking about, okay? That's, you know, here's the professor, 2 pi later, there's minus the professor, okay? Doesn't look any better than plus, right? All right, so that's, I think, a good lesson for this business of things. But also, and this is the other thing that's interesting, is you take any of these ratios that we have produced for one frequency versus the other, take that ratio, and if that ratio is rational, you'll get a closed curve. That's perfect mechanical, classical mechanical periodicity, which is something that turns out to be of use for getting certain kinds of quantum wave functions that have scars caused by a classical trajectory that's just being played over and over and over. It cuts a groove in the wave, like somebody that's driving a car in a field and always going on the same path. Eventually you have a groove there. So getting a rational periodic point in the phase space is very important. So this is the basic idea here, is you just keep going. You take the number that you've got for your ratio, and here's pi, that's very irrational, so that will never stop. But it still gives you, what you do is you take the integer of that. That's, you throw everything away except the 3, okay? And then you make something out of that. You write the A1 as the A0 minus the number that you had. In other words, 3 point minus that. And then you divide by that, 7.6, slop that off, and that's your next integer right here. So basically you're taking pi and writing as 3 and 1/7, so everybody learns that one. But here's the next stop, is 3 1/7 plus 1/15, which is what you're going to get as you play with this number right here. So you ever done this before? Have you ever seen this? This is really, if you're going to do quantum computing, you got to know about this kind of stuff. This is number theory, okay? So I keep going here, and you see pretty soon I'm doing pretty good. I'm getting 3.141. 509, the O is wrong, okay? I should have a 9 there and 2, and that last one is probably wrong. But we're getting real accuracy at every time. Now, suppose you take the golden mean. What's it, you know, it's got a lot of numbers in there, kind of like that one does. And the one that's really fun to take, and I should have given this as a problem, you ought to do it if you want extra credit, partial fraction E. It's bizarre, absolutely bizarre what happens. But anyway, this one, look at it. I get all the way down to the bottom there, and I barely have two-figure accuracy, two-figure precision. That's why I say I always put, when I'm doing beats for somebody, I always put golden ratio in so they don't ask questions about the patterns I'm getting here. Then, you know, then I show one with patterns, and you can talk about the patterns, but you got to get the beats past, you know, the discussion first. So what I should do here is get back, make sure I'm back here. Yeah, here we go. This is a continued fraction of the omega 1, 2.31, and 1.89. Just numbers to pick out of a hat. And what we're talking about at this point is a 5-to-4 ratio. That's pretty close to the ratio of those two. And what 5-to-4 means is when I count the number of crossings, 1, 2, 3, 4, 5 on this axis, and compare it to the crossings on this axis right here, 1, 2, 3, I should say 1, 2, 3, 4. Ooh, didn't count. I shouldn't probably have counted that one. But in any case, it's very close to 4:5 ratio, but not that close, because I've got to get down to 1.22222. That's what this thing actually comes out to be as a rational on this particular choice. Okay, and since they're only three-figure numbers, you've got to have rationality fairly quickly. The next stop on this here is 6:5, and I believe that's what I mean, 1, 2, 3, 4, 5, and that seems to be the same thing. I'm a little confused. Compared with 1, 2, 3, 4, 5. So yeah, that makes sense. 6:5 makes sense. And then we have one more, 11:9. If you let this thing go, this is pretty much it, because the next stop here, the rational fraction program goes crazy. So this one has 11, I think it's this one, 11 to 9. This is your ratio. Okay, so that's pretty much it. Now the C, guys, this is weird. This, of course, is what happens when you put Coriolis forces on an oscillator. So here is the spin vector going through A to B to minus A, which is the orthogonal state, that's up and down, and then coming around again right there, and it was pi out of phase. I don't know if you noticed it, but that has to go again before it comes back right about here. So that's going to happen, and you can see that pretty easily just by looking at the diagrams, and I'll do that in a minute. This one goes quite a long way, and now we start looking at ratio of cuttings across a radius versus an angle, and that is going to be leading some pretty big numbers, 831 to 791 in that particular counting. Okay, let's stop for a minute here. I'm going to erase the paths, and I'm going to start by putting a vector right about there, and you can see I'm pretty close. Well, no, it's moving on me. I don't know why that is. That's a weird phenomenon. We should fix that.
I didn't quite catch it.
If you set your initial condition, it starts to eat it. Let's reset to equals or pause, erase paths, and start again. With a slower. I'm going to do it slower. So I'll get that guy slowed down here. Okay, resume. I've erased paths, and we ought to fix it so in your erase paths it actually does erase at that moment. But anyway, here I'm going to just start right here and go to this point, and as long as I don't move it, I can probably get the thing to go. Now it's pretty lousy. Somehow it has other components. It's not really obeying the thing. But that's pretty close to a circle, and you can see how far I am.
If you true up on it, it'll work, I'm sure of it.
Pardon?
Just true up on it and say like start on one of those, you know, unit points, and then observe
right
the output as it's dragged, and it'll say unit TM a little bit further.
There we go.
It's good enough for
That's
government
close
work.
enough. Okay. So
Not true. Okay.
something's wrong.
That's now that gives me my clue what to chase down at home.
Yeah, that one, that's not right. You can see it was running all over the place there. It's close to circular, but something screwy going on there.
I
should
would
be able
just hit reload and try it again.
Yeah. Yeah, I got.
Now you've got about 12 windows up and running. Even if they're idle, they actually take up resources. It's all those
So
need to be
here's
killed.
the. Well, you know what's happening every time I do that? I think it's funny. Let me go ahead here, and I'll just go to there. and see if I can get.
See, you're not on the 1 up top,
Oh,
so it's going to be elliptical. You needed to start on the 1.
Yeah, something's really.
But make the x-coordinate 1 and the momentum 1, and it should.
Next has paused.
What?
I'll go the other way this time just to see if I get the S vector.
There you go.
It looks like the S vector is pretty close to there, so we should. There we go.
Yeah, see, we weren't starting on the 1. That's it. That's why I was elliptical.
Yeah. It should make it. See, there's just a tiny little residue pattern in that one, a little bit of beading that's left. But that's pretty close to an eigenvector for C motion. Okay.
Remember, you can right-click over in that field, and it would make it exact. Your high and your low.
Oh, okay, that's something I didn't know.
There's needs documentation.
Let's go.
See, and you can also hand key them in exact there, so you wouldn't have any issues as well.
Yeah. Anyway, that's typical. By the way, this is the kind of motion a Foucault pendulum makes. I've been to a museum where they have a pendulum in a big tower or a big room, right? You let it go, and depending on your latitude, it goes like this and slowly moves around, just exactly the motion that we see in that. Now, this is where it gets weird when you do both at once. When you talk about something that's not on the axis like that, and if it's on the AB plane, then it's going to be linear polarization, and all you'll be doing is keeping a potential and rotating. But if you start to go in a C direction, either positive or negative, it's a whole other ballgame. That's not something that's easy to do in classical mechanics. And quantum mechanics is just as easy as all the other stuff. So this is an important part of the thing. There's an example that's really simple, just a little bit of tipping on the V. And this is what's, really takes another thought. This is the famous avoided crossing that occurs for the eigenvalues of a system like this, where I change the A and the B. I start with the thing being perfect here with B right at there. That's our two-state system with bilaterally balanced, and I unbalance it by making these different. So I increase the A on this side and make D small, much less than D, and on this side do the opposite. There's a little A over here, and a big D to make, and it makes this huge delta, I should say, this whole huge gap, much bigger than what I had here. And the arithmetic for this is really kind of neat. You take a transformation that would diagonalize a balanced matrix, but it completely messes up the A minus A part of it as you apply that thing. I'm just doing the matrix arithmetic here, and I get this, which is this. So what this transformation does, and this is question marks, there's the answer. It takes the B's and replaces the one A's, and the A's are replaced by B. Okay, so we used to have plus A and minus A, now plus B and minus B. So that's worth knowing. Now this is so important to physics because it's the motion and the dynamics associated with changing this that led to the discovery of the laser. It wasn't a laser, it was a maser. Charlie Towns, MIT, just playing with radar equipment that came off of the warships. This is another example of where stuff left over from the war is very useful. So we take this view of a nitrogen atom being either down or up between three hydrogens, and we then look at the energy levels as a function of something that will pull differently on one of the eigenstates than the other. And so that is the whole idea. Now you can do this with perturbation, or you will fail. This is a good example of why perturbation theory is not. But anyway, this is a picture of the thing as I change the tunneling amplitude, and this is where you do the change of the electric field. And all kinds of engineering goes into doing this and what you get from it. So this will always be a ground eigenstate. This will be an excited one, but they'll be very far apart as you move out into a higher electric field. There'll be a perfect B-type symmetry right here, and then it'll go the other way. And we used to call this a diabolo, which is a top that is shaped like that. When kids play with it, they throw it up on, have it stick with the string, and you get it spinning by doing this, and then you throw it in the air and it maintains its orientation, pretty much. It might wobble a little, and you catch it. Ever see that game played? It's not done so much in this country. They're all sitting there doing electronic games. But in other countries where they can't afford that, that's played all the time. I was in Brazil, I saw it all the time. It's now called Dirac point. And this is what this old building works on now, Dirac points. So, you know, this is something else that ties us in. Anyway, there's lots more to look at in this particular lecture. I knew I'd get out to this point and be over time, but I think it's worth it. It's something that we've got to go on, but there's a heck of a lot of physics waiting still to be discovered about this sort of thing. And I encourage you to play with the diabolo and the triabolo. There's a whole this as you go to higher and higher size matrices, each time you increase the dimension, a whole new bunch of phenomena say, hey, look at me, I'm cool. Okay, we'll see you next Monday, and we'll talk about parametric resonance, which is really crazy.